Hey guys, welcome to Safi Next. In this video I want to use a geometric approach to prove the double angles formulas for sine function and cosine function. That is, I want to prove these two formulas by using a geometric approach. In the geometric approach I consider a circumscribed rectangle and an inscribed right triangle. So to begin with, I first draw a rectangle of the form this, whose vertices I denote with A, B, C and D, and then from vertex D I draw a line on side AB and represent the point of intersection with E, and I assume that the angle made by DE with side AD equals alpha. Then I draw another line from point E on side BC and represent the point of intersection with F, and I draw side EF in such a way that it makes an angle 90 degree with side DE. So I consider the angle at vertex E is in fact 90 degree. Then I join vertex D to point F and I construct an inscribed right triangle in the form of DEF. So DEF is an inscribed right triangle in circumscribed rectangle ABCD. I also consider that the angle at this position is equal to beta. Then from triangle DEF we can see that this side, that is DE, is base of the triangle and EF is the perpendicular, because we have 90 degree at this position, so these two sides are perpendicular to each other, but we know the angle at side DE, therefore the side DE makes the base of this right triangle and EF makes the perpendicular and DF is the hypotenuse. And we know from trigonometric ratio, from the side ratio of the right triangle, that the base can be expressed in terms of the hypotenuse and angle beta in the form DE equals DF times cos of angle beta. And similarly I can write a relation for EF in the form EF equals hypotenuse times sine of the angle beta, that is DF sine beta. Then from triangle DAE, that is from triangle DAE, we see that this is 90 degree and we know the angle at point D, so side DA is the base of triangle DAE and side AE is the perpendicular of this triangle, and similarly DE is then hypotenuse for triangle DAE. And if I want to extract the base and hypotenuse of this triangle in terms of its hypotenuse, I can write this as in the form DA or AD equals DE, that is hypotenuse times cos of angle alpha. And if I use the value of DE from equation 1, I can write AD equals DF cos beta times cos of alpha, that is, this is DF cos of beta is the value of DE at this position. Similarly, for the perpendicular AE, I can write AE equals DE times sine of alpha, that is hypotenuse times sine of alpha. And again, using the value of DE from equation 1, I can rewrite this relation in the form DF cos of beta times sine of alpha. Now we define the angles at point E at this side and at this side to be theta 1 at this side and theta 2 at this side. Then from the geometry of this line AD, I can write theta 1 plus 90 degree plus theta 2 equals 180 degrees. That is, I can write theta 1 plus theta 2 plus 90 degrees equals 180 degrees, and taking the 90 degrees to this side would make 180 degrees minus 90 degrees equals 90 degrees, and taking theta to this side would make it minus theta. So from this equation I can write theta 2 equals 90 degrees minus theta 1. And similarly, from triangle DAE, we see that the sum of all the three angles should be equal to 180 degrees. Therefore, I can construct an equation theta 1 plus alpha plus 90 degrees equals 180 degrees. That is, from triangle DAE, I can write theta 1 plus alpha plus 90 degree equals 180 degrees, and taking 90 degrees to this side would make this side 180 degrees minus 90 degrees, which is equal to 90 degrees, and therefore I can write theta 1 in terms of alpha in the form of 90 degrees minus alpha. And if I put the values of theta 1 in equation 5 at this position, that would make 90 degrees minus 90 degrees plus alpha. The 90 degree will cancel with 90 degrees, and ultimately I'm left with theta 2 equals alpha. So this angle theta 2 is in fact equal to angle alpha at this position. So I replace theta 2 with alpha. Now I turn my attention to triangle EBF, and from triangle BEF or EBF, I can see that this is 90 degree at vertex B is 90 degree. So and we know the angle at side EB, therefore side EB or side BE is base of this triangle, and BF is the perpendicular of this triangle, and I can express the base and perpendicular in terms of the hypotenuse EF and angle alpha in the form of EB or BE equals hypotenuse times cos of alpha. And if I use the value of EF from equation 2, I can re-express this in the form of BE equals df sine alpha, where df sine alpha is the value of EF at this position, and times cos of alpha. Similarly, for the perpendicular BF or FB, I can write EF sine of alpha, that is the hypotenuse times sine of alpha, sine of this angle. And using the value of EF from equation 2, I can rewrite BF in the form of DF equals sine of beta cos of sine of alpha, where DF sine of beta is in fact the value of EF at this position. Okay, now let me call this angle gamma, and then from this geometry this whole angle is 90 degree. Therefore I can express gamma in terms of alpha and beta by writing the equation gamma equals 90 degree, that is this whole minus beta minus alpha. So I can construct this equation, and then from triangle DCF, this angle at vertex C is 90 degree. Therefore I can write this angle in terms of alpha beta using the value of gamma, because the sum of gamma plus 90 degree and this angle would be equal to 180 degrees. Therefore I write an equation of the form, since this is 90 degree, I can construct this equation angle FDC, that is the angle at this point, plus angle DFC, that is the angle at this point, plus angle DCF, that is the angle at this point or this vertex. So the sum of these three angles is 180 degrees. And if I put the values, angle FDC is gamma, and gamma is equal to 90 degree minus alpha minus beta, and angle DCF is in fact angle 90 degree, which is angle C. So I put these two values at this position, in this position, and can find the value of angle at F. So I can write this is the value of this angle. I write this at its own place, and for this I write 90 degree. So 90 degree plus 90 degree is 180 degree, and taking that 180 degree to this side would cancel with this 180 degree. That means I can write angle DFC equals alpha plus beta. So this equation reduced to this form, alpha plus beta. Therefore I can write this angle equal to alpha plus beta. Now from triangle DCF, I can construct two other relations, and since this is 90 degree and I use this as the base angle, so this side DFC is the base and DC is the perpendicular of this triangle with DF equals hypotenuse. Therefore, I can write FC, that is the base, equals hypotenuse times cos of this angle. That is, I can write FC equals DF times cos of alpha plus beta. And similarly, I can write DC equals hypotenuse times sine of this angle. That is, I can write DC equals DF sine of alpha plus beta. Now we have developed all the needed equations and we can put them together to prove these two relations. And that we can do, since DC is exactly equal to AB, and I can write AB equals AE plus EB. That is, I can write DC equals AE plus EB. And we know the values of DC, AE and EB. From equation 8, I have DC equals this thing. From equation 4, I have AE equals this thing. And from equation 6, I have BE or EB is equal to this thing. So putting the values from equation 9, equation 4 and equation 6, in this equation I can write for DC I write DF sine alpha plus beta, for AE I write DF sine alpha cos beta from equation 4, and for EB I write DF cos of alpha sine of beta from equation 6. Now since each term carries DF, therefore I can cancel DF from every term, and that leaves me with sine of alpha plus beta is equal to sine of alpha cos of beta plus cos of alpha sine of beta. And this is exactly this first equation. So we have proven the double angle formula for sine function from this geometry. Now I remove this and now use this one relation FC. From this I can write BC equals BF plus FC, or CF plus FB equals BC, and BC is exactly equal to AD. So I construct this one relation. CF plus FB, that is CF plus FB equals CB, and CB in turns equal to AD. So this is equal to AD. And now from equation 3 we have the value of AD. From equation 7 we have the value of FB, and from equation 8 we have the value of CF. So putting these values from these three equations, I can write DFO. Let me first set the equation into this form. CF equals AD minus FB, and now putting the values from this equation, I can write DF cos of alpha plus beta from equation 8 for CF, DF cos of alpha cos of beta from equation 3 for AD, minus DF sine of alpha sine of beta from equation 7. So again, every term carries DF, therefore I can cancel that out from both sides, and that leaves me with cos of alpha plus beta equals cos of alpha cos of beta minus sine of alpha sine of beta, and this is exactly this second one equation. So we have proven the double angle formulas for sine function and cos function from a circumscribed rectangle and an inscribed right triangle geometric setup. Thanks for watching.